Did you know that oil is often called black gold? A precious gift of nature that has helped power the entire modern civilization, yet has also been linked to numerous conflicts throughout history. And even today, humanity has yet to find an energy source that can truly replace it. So how is it possible that every year humans extract more than 4 billion tons of crude oil from deep beneath the Earth's surface? An enormous volume so vast that it could theoretically fill an entire state like Texas with a sea of oil. The journey begins within ancient sedimentary layers beneath the ocean floor, where the remains of microscopic organisms accumulated over hundreds of millions of years, gradually forming vast oil reservoirs buried kilometers underground. Using ultra-hard diamond-tipped drill bits, humans bring this hidden resource to the surface and send it to massive refineries, where it is transformed into gasoline, diesel, jet fuel, plastics, and thousands of industrial products that power the modern world. Today, join Agriculture Insight as we explore the remarkable journey behind the oil industry, a source of energy that now sits at the heart of global economic shifts and geopolitical competition. The true turning point of the modern American oil industry came in 1901, when the Spindletop oil well in Texas suddenly erupted, shooting oil more than 45 meters into the air and producing up to 100,000 barrels per day. This event sparked the Texas oil boom and marked the beginning of the explosive growth of the oil and gas industry in the United States. Today, the United States is the largest oil producer in the world, with production reaching nearly 13 million barrels per day. Among all states, Texas plays the central role, producing over 40% of the nation's total oil output. Some even say that if Texas were an independent country, it would rank among the world's top oil-producing nations. However, the United States is also the largest consumer of oil on the planet, despite having only about 4% of the world's population, a relatively small share compared to its enormous energy consumption. As a result, fuel prices in the U.S. are a highly sensitive economic issue. When fuel prices rise, transportation and goods become more expensive, which directly affects inflation and can even influence elections. To protect its energy security, the United States established the Strategic Petroleum Reserve, the largest emergency oil reserve in the world. It can store more than 700 million barrels of oil in massive underground salt caverns. This system was created after the 1973 oil crisis, ensuring that if global oil supplies are disrupted, the U.S. economy would still have enough energy to keep running. For this reason, oil is not just a fuel, it is also a strategic resource closely tied to the economic and political power of the United States. Now let's travel back hundreds of millions of years to see how the black gold that powers our world today was truly formed. Around 100 to 300 million years ago, ancient oceans were filled with countless algae and microscopic marine organisms. When these organisms died, their remains sank to the seafloor and were gradually buried beneath layers of mud and sediment. Over time, the immense heat and pressure deep within the earth transformed this organic material into hydrocarbons, the fundamental components of crude oil. These hydrocarbons then migrated through porous rock layers and became trapped in geological formations known as oil traps, deep beneath the ground or ocean floor. After accumulating for hundreds of millions of years, they formed vast oil reservoirs that today require drilling as deep as 10 to 12 kilometers into the earth to reach. But how do humans manage to find oil reservoirs buried kilometers beneath the Earth's surface? The answer begins with the stage known as oil exploration. Long before any drilling rig appears, geologists must first see deep underground using seismic surveys. Specialized vessels send powerful sound waves down into the ground or the ocean floor. When these waves encounter different rock layers, they bounce back and are recorded by thousands of sensors. Using this data, computers construct detailed 3D maps of geological structures located 2 to 5 kilometers beneath the surface. Even so, searching for oil remains a high-risk endeavor. On average, only about 1 out of 10 exploration sites ultimately contains oil in quantities large enough to be commercially viable. But if a promising oil trap is discovered, the reward can be enormous. Such a reservoir may hold hundreds of millions of tons of crude oil, a massive energy resource capable of powering entire economies for decades. Most offshore drilling rigs are constructed in large shipyards and industrial ports, where massive steel frameworks are welded together into modules. A single rig can weigh 10,000 to 30,000 tons, equipped with a towering drill derrick, heavy cranes, power generators, living quarters, and even a helicopter landing pad. Essentially, a small industrial city at sea. Once completed, the entire structure is transported by heavy lift barges or specialized vessels to the oil field, often located 100 to 300 kilometers offshore. At the site, engineers lower the steel jacket structure to the seabed. Giant steel piles, sometimes over 100 meters long, are driven deep into the seabed sediments and secured with concrete to create a stable foundation. After that, the deck of the drilling platform, weighing thousands of tons, is carefully lifted and placed onto the jacket using super heavy cranes with remarkable precision. Only when this steel city is fully installed amid the waves of the open ocean can drilling operations finally begin, opening the path to oil reservoirs hidden kilometers beneath the Earth's surface. Once the drilling platform is firmly anchored in the ocean, the real work begins: drilling the oil well. From the top of the derrick, which can rise dozens of meters high, steel pipes about 9 to 10 meters long are connected one by one to form a massive drill string that slowly penetrates deep into the earth. At the tip is an ultra-hard alloy drill bit that rotates continuously, crushing ancient rock layers located 2 to 5 kilometers beneath the surface. Throughout the process, a special fluid known as drilling mud is pumped constantly down the well. It acts like the lifeblood of the drilling system, cooling the drill bit, stabilizing the well walls, and carrying rock cuttings from deep underground back to the surface for engineers to analyze. Drilling a single well can take several weeks to several months, and offshore projects can cost 50 to 100 million USD per well. Today, many wells are not drilled only vertically, but also horizontally, for an additional 1 to 3 kilometers, allowing access to more oil-bearing layers within the same reservoir. But at these depths, geological pressure can exceed 10,000 psi, hundreds of times greater than atmospheric pressure. For that reason, every meter of drilling must be carefully controlled, because even a small mistake can trigger a dangerous oil blowout. When the drill bit finally penetrates the oil-bearing rock layer, the well enters its most critical stage: oil production. Inside the well, engineers install production tubing to channel the fluid from several kilometers underground up to the surface. In many newly discovered reservoirs, the natural pressure within the oil-bearing formation can be strong enough to push the oil upward on its own, like a massive underground spring suddenly released. However, this natural flow usually lasts only during the early stage of production. As reservoir pressure gradually declines, mechanical pumps or electric submersible pumps (ESP) are installed to maintain the flow. A modern industrial pump can lift 15,000 to 20,000 barrels of oil per day, operating continuously several kilometers beneath the Earth's surface. It's important to note that the fluid rising from the well is not pure oil. Instead, it is a mixture of crude oil, natural gas, water, and fine sand carried up from the surrounding rock layers. For this reason, at the drilling platform or nearby gathering station, the mixture is directed into high-pressure separators, where oil, gas, and water are separated into different streams. This is the first stage of processing, before the crude oil is sent through pipelines and continues its journey to oil refineries. When the fluid from an oil well reaches the surface, it is not pure oil but a mixture of crude oil, natural gas, water, and fine sand. In many oil fields, the actual oil may make up only 60 to 70% of the mixture, while the rest consists of water and gas. For this reason, the mixture must first be sent into high-pressure separators installed directly on the drilling platform. Inside these separators, the pressure is reduced so that the components can separate naturally based on density. Natural gas, being the lightest, rises to the top and is collected to be compressed into gas pipelines or re-injected into the reservoir to maintain pressure. Crude oil forms the middle layer and is directed into temporary storage tanks. Meanwhile, water and sand, which are heavier, settle at the bottom and are removed for separate treatment. After this initial separation, the crude oil becomes stable enough for transportation. It is then pumped into subsea pipelines stretching hundreds of kilometers or transferred to oil tankers capable of carrying millions of barrels, beginning its journey to refineries on land where it will be transformed into gasoline, diesel, and many other petroleum products. Not all oil reserves lie beneath the ocean. On land, oil extraction takes place in a more familiar setting but remains just as complex. Once a well reaches the oil-bearing layer, crude oil is brought to the surface through production tubing. In the early stage, natural pressure in the reservoir may push the oil upward on its own. But as the pressure declines, mechanical pumping systems begin to take over, the most recognizable being the pump jack, the machine with a rhythmic metal arm often seen in onshore oil fields. Each pump jack works like a giant underground syringe, drawing oil from depths of about 1 to 3 kilometers below the surface. A typical onshore well can produce 20 to 300 barrels of oil per day, depending on the size and richness of the reservoir. In major oil regions, such as the Permian Basin in Texas, where more than 7,000 wells are currently operating, thousands of pump jacks move up and down day and night, forming vast fields of pumps stretching across the landscape. The fluid brought to the surface is still a mixture of oil, gas, and water, so it must first be separated at nearby gathering stations before the crude oil is sent through pipelines or tanker trucks to refineries. From these slowly moving machines scattered across dry fields, a resource formed over hundreds of millions of years begins its journey into the modern global economy. After leaving the oil fields, crude oil is transported to oil refineries, facilities where one of the most complex industrial processes in the world takes place. A large refinery can process 300,000 to 600,000 barrels of crude oil per day, operating continuously around the clock. The most important step in this process is fractional distillation. First, crude oil is heated to about 350 to 370 degrees Celsius, turning it into vapor before it enters a distillation tower that can rise dozens of meters high. As the vapor moves upward inside the tower, different hydrocarbon compounds condense at different heights depending on their boiling points. The heaviest fractions, such as asphalt and lubricating oils, condense near the bottom. Above them are diesel, followed by kerosene and jet fuel, while gasoline condenses closer to the upper levels. At the very top of the tower are light gases such as propane and butane. However, the products obtained at this stage are still not fully ready for use. Many hydrocarbon molecules remain too large or do not yet meet fuel standards. They must undergo further processes such as cracking, which breaks large molecules into smaller ones, reforming, which improves fuel quality, and blending, where different components are mixed to meet precise technical specifications. Through this chain of processes, a single 159-liter barrel of crude oil can be transformed into gasoline, diesel, jet fuel, and thousands of petrochemical products that power the modern global economy. During the extraction of petroleum, crude oil is often produced together with large amounts of natural gas. When oil companies do not yet have the infrastructure to capture or transport this gas, they carry out a process known as gas flaring, which involves burning the excess gas on tall flare stacks at the oil field. This practice helps reduce pressure in the well and ensures safety by preventing the buildup of highly flammable gases. However, gas flaring is controversial because it releases carbon dioxide and other greenhouse gases into the atmosphere, while also wasting a valuable energy resource that could otherwise be used to generate electricity or fuel. As a result, in recent years, many countries and oil companies have been working to reduce gas flaring by capturing and utilizing the gas instead of burning it. Now we take you to Diavik, one of the few diamond mines in the world located beneath the frozen waters of the Arctic. Amid temperatures plunging to -30°C and relentless storms, this site stands as both an engineering marvel and a convergence point for diamond-bearing ore bodies formed 150 kilometers deep within the Earth, under temperatures of around 1,000 degrees and pressures reaching 50,000 atmospheres. After billions of years in the mantle, only a small fraction of these diamonds were carried to the surface by ancient volcanic eruptions, becoming trapped in kimberlite rock, the very target of mining projects worth hundreds of millions of dollars, where humans challenge nature itself to lay their hands on these hidden treasures. Diamond mining begins with high-precision geological exploration. Satellite imagery, gravity sensors, magnetic surveys, and indicator minerals such as garnet and ilmenite are used to trace kimberlite pipes hidden deep underground. But the odds are brutally low. Out of every 1,000 structures identified, fewer than 1% contain sufficient reserves to become a commercial mine. In the world of diamond mining, everything begins with an explosion. Once a site is confirmed, extraction proceeds using one of two main methods, depending on the depth of the ore. At open pit mines, massive spiral-shaped pits are carved into the ground, some stretching up to 1 kilometer wide and plunging more than 500 meters deep. Mining here follows a strict cycle. First, drilling rigs bore hundreds of blast holes, each with carefully calculated depth and angle according to engineering design. These holes are then loaded with bulk explosives, most commonly ANFO, a mixture of ammonium nitrate and fuel oil, chosen for its powerful blasting capacity and relatively low cost. The charges are detonated remotely using delayed blasting techniques. This method must not only fracture the rock, but also precisely control ground vibrations to protect pit walls and prevent diamonds inside the rock from cracking. Immediately after the blast, tens of thousands of tons of broken rock are loaded onto ultra-class haul trucks, machines as tall as two-story buildings, capable of carrying up to 450 tons per load, and transported to the surface. For deeper deposits, underground mining methods are employed. Instead of excavating from above, engineers construct a network of tunnels beneath the ore body, then blast the lower sections, allowing the entire rock mass to collapse under gravity. Workers and machinery operate in narrow tunnels, extending from 700 to more than 1,000 meters below the surface. These are extremely harsh environments, where rock temperatures can reach 40 degrees Celsius, requiring massive ventilation and cooling systems to continuously pump fresh air down from above. But deep underground, danger is always close at hand. In 2017, the Mir diamond mine was struck by disaster when water from an overlying lake suddenly flooded in, breaching protective barriers within seconds and leaving the world's second-largest diamond mine paralyzed for years. Despite all these immense efforts, diamond mining efficiency remains astonishingly low. On average, more than 250 tons of earth and rock must be excavated, transported, and crushed to recover just a single carat of diamond, barely larger than the tip of a pencil. Once brought up from deep underground, tens of thousands of tons of kimberlite ore are hauled by heavy trucks directly to centralized processing plants. It is here that the rock enters a vast automated system, marking the beginning of the process of extracting its most valuable crystals. Massive crushing machines, each weighing dozens of tons, play a central role in breaking down large blocks of ore. Operating like steel jaws, they are powerful enough to crush even granite. Yet despite their absolute hardness, diamonds are extremely brittle. A misdirected impact can shatter a crystal structure into fragments, completely destroying its commercial value. For this reason, crushing forces must be calculated with extreme precision. Strong enough to break the surrounding rock, yet gentle enough to protect the crystals within. The process is carried out in multiple stages, beginning with slow compression using heavy roller presses, followed by roller crushers, and concluding with vibratory separation to maximize recovery efficiency while minimizing risk to the gemstones. After crushing, all fragmented material moves into the cleaning stage, where clay, mud, and fine dust are removed from the ore. If not thoroughly eliminated, these binding materials can clog machinery and interfere with modern separation systems. Industrial washing units use large rotating drums, multi-deck vibrating screens, and high-pressure water jets to create turbulent flows that scrub the material clean. At this stage, particles smaller than 1 millimeter are completely screened out, as their likelihood of containing diamonds is extremely low relative to the cost of processing. But for commercial-grade diamonds, the journey is only halfway complete. Their true value is unlocked inside the cutting workshop, where each rough stone is examined, evaluated, and cut with absolute precision to become a gem of near-perfect brilliance and balance. Every diamond is entirely unique. No two stones are ever exactly the same. That is why, before cutting begins, specialists perform a full 3D scan of each rough diamond to analyze its shape, internal flaws, clarity, and the way it reflects light. This data is then fed into specialized software to calculate the most efficient and valuable cutting options. Some diamonds are divided into multiple smaller stones to maximize profit, especially when internal imperfections make crafting a single large gem less viable. Others, particularly rare or exceptionally clear stones, may be kept intact to create a one-of-a-kind piece. Every decision at this stage is driven by a single goal: to unlock the diamond's full potential by balancing brilliance, symmetry, color, and weight. The aim is to produce a stone that sparkles with maximum intensity, displays optimal color, and retains as much mass as possible, while honoring the natural beauty that took billions of years to form. Once the evaluation and planning stages are complete, the rough diamond enters its most critical phase: cutting and polishing. The process begins with preliminary cutting using high-power lasers, accurate to within 0.001 millimeters. The laser targets the stone's weakest structural points, allowing it to be shaped or divided without causing unintended fractures. This is followed by manual grinding and polishing. Master craftsmen use polishing wheels coated with diamond dust, because only diamond is hard enough to shape itself. Throughout this stage, pressure, contact angle, and rotational speed must be constantly adjusted to ensure each facet meets precise geometric proportions. The entire process typically takes between 3 and 8 weeks, depending on the stone's complexity. The final result is a flawless structure, with facets engineered to reflect light at maximum intensity, creating the distinctive brilliance that defines a diamond. Once its shape is complete, a diamond is not released to the market immediately. It must first undergo a rigorous grading process at specialized laboratories. Here, the stone is examined under advanced microscopes to assess 4 core criteria: color, clarity, carat weight, and cut quality. Even microscopic carbon specks or ultrafine surface blemishes are recorded, as they ultimately determine the diamond's final commercial value. If the stone meets these strict standards, it receives a unique digital signature, a laser-engraved identification code etched directly onto its outer edge. Invisible to the naked eye and readable only under high-magnification microscopes or loupes, this code serves as a critical key for traceability and absolute transparency. Finally, trusted institutions such as the GIA issue an official digital certificate, a comprehensive identity record permanently stored within a global system. In essence, this certificate is the diamond's passport, verifying its quality and safeguarding its value on the international market. Once certified, a diamond enters its final stage, becoming the centerpiece of a global jewelry market worth more than $300 billion each year. At major houses such as Cartier and Tiffany & Co., craftsmanship demands absolute precision, from casting and setting to meticulous hand finishing. To maximize light performance, artisans favor techniques like hidden settings or pave mounting, minimizing the amount of metal that obscures the stone's surface. The goal is to secure the diamond firmly while allowing light to pass through and refract from every possible angle. The result of this uncompromising process is a product with near eternal durability. In reality, gold can be scratched, melted, or worn down by mechanical stress over time, but a natural diamond cannot be destroyed by such ordinary forces. That is why a diamond worn by a bride on her wedding day can remain perfectly intact, even when passed down through dozens of generations. Do you know what truly gives a dollar its value compared to an ordinary piece of paper or cloth? It's not the ink, nor the imagery, it's the design. A sophisticated security architecture embedded in every tiny detail. Before any bill comes into existence, its journey begins with a sketch created by the most skilled engravers at the U.S. Bureau of Engraving and Printing, B. Every element, the presidential portrait, the phrase "In God We Trust," geometric patterns, or the blank space for a watermark, is designed as a layer of security. These experts are bound by lifetime confidentiality, even after retirement, because revealing a single detail could provide counterfeiters with a critical loophole. Once the sketch is finalized, it is transformed into an ultra-high-resolution laser engraving, ensuring that each denomination has a completely unique set of identifiers. But design is only half the story. The rest begins in the cotton fields of the southern United States. Over 2/3 of a US dollar structure is made from cotton, a special fiber that forms a steel frame giving the bill strength, durability, and near-tear resistance. To achieve this quality, the US doesn't use ordinary cotton. They grow specialty cotton in southern states like Texas, Mississippi, and Georgia, where the hot, humid climate produces long, pure white fibers far stronger than standard textile cotton. During harvest, high-capacity machines collect more than 2,000 kilograms of cotton per hour, but only about 10 to 12% meets the standard for currency production. The bales are then sent to processing plants, where the entire production line operates almost entirely automatically. Machines remove plastic wrapping and feed the cotton into the system. Rotating shafts with cone-like teeth fluff the fibers, removing dry leaves, small stems, and dirt. Next, compressed air and vibration mechanisms clean fine dust before the gin separates the seeds, keeping only the purest layer of fiber. While the textile industry allows up to 5% impurities, cotton for currency can contain no more than 1%. Even a tiny piece of leaf the size of a pinhead can cause the system to reject an entire 200 kilograms bale. Everything must be perfectly clean before being sent to the paper mill. To increase durability and resistance to twisting, the U.S. also adds linen fibers. Most of the linen for U.S. currency is imported from France and Belgium, where centuries-old flax fields produce long, fine, and exceptionally uniform fibers. The flax is harvested using specialized machines that pull the entire plant from the ground rather than cutting it, preserving the full fiber length, a key factor in a bill's strength. Bundles nearly 1 meter long are laid in parallel on the fields to air dry naturally for several weeks. Once the fibers reach the ideal ripeness, machines roll them into large bales weighing around 300 kilograms. From there, the flax undergoes a sophisticated processing routine to extract the fibers perfect for currency paper. In the fields, it is left to rot naturally for 2 to 4 weeks, a form of biological soaking where bacteria and natural yeast break down the plant's pulp, separating fibers without breaking them. An interesting fact, the retting process must be monitored daily. Extending it by just 48 hours beyond the ideal can weaken the fibers by 20 to 30%, enough for them to be rejected for currency production. Finally, the flax passes through crushing and combing machines, which remove the woody core. The resulting high-quality fibers are pressed into bales and sent to the paper mill. When the raw cotton and flax bales arrive at the mill, the journey to create the world's most secretive paper officially begins. The white fibers are cleaned with steam, chopped, and blended in large vats like a thin porridge, where ultrafine security fibers and invisible industrial DNA are mixed in, forming a base that no counterfeit printer can replicate. The mixture is then poured onto conveyor belts, pressed thin, dried, and rolled into large sheets of paper. Each sheet already contains watermarks, security threads, and extremely precise technical features. The paper is then dried, pressed, cut into large rolls, and sent to the U.S. Bureau of Engraving and Printing, BEP. This is a proprietary security paper, never sold on the open market, and only Crane Currency in Massachusetts is authorized to produce it under contract with the U.S. government. The paper is ready, but a dollar truly begins to exist only when the steel engraving is created. In the BEP's engraving room, artisans sit before gleaming steel plates, using pantograph pens to carve every detail, so meticulously that some spend 3 weeks perfecting a single strand of hair. From Franklin's forehead wrinkles to the tiniest decorative patterns, every line must be absolutely precise. Once completed, the master plate is chrome-plated to withstand tons of printing pressure. Even a deviation smaller than a hair can result in its immediate destruction. But one engraving alone is not enough. From the master, the steel plate enters the serography system, where every detail is copied so precisely that the human eye cannot distinguish it. The plate is then coated with fluorescent powder, exposed to UV light to reveal the image, and placed in an electroplating bath, where electric currents carve grooves just a few microns deep. The result: electroplated steel plates that are 20 times more durable than the original, able to endure tens of thousands of printing cycles under tons of pressure. Each plate perfectly identical and ready for the currency printing line. Once the steel plates are ready, another production line simultaneously kicks off. Offset printing to create the first background layer of the bill. This initial layer forms the colored background, including watermarked patterns, light color overlays, and decorative borders. At this stage, high-speed printing machines print both sides of the paper simultaneously using special inks. The ink is transferred from the printing cylinder to an intermediate rubber layer, then pressed onto the paper fibers, ensuring even adhesion and sharp, precise details. This technique is applied only to denominations $2 and above. The $1 bill skips this step entirely, which is why it feels different to the touch. The personnel working in the currency printing facility are among the most rigorously vetted in the U.S. Spotless backgrounds, pass lie detector tests, and possess ultra-fine precision skills. All activities are monitored 24/7, and AI is allowed only to assist, never replace human operators. After the background layer is fully dried, the sheets are stacked and sent to the intaglio printing stage. Using the hand-engraved steel plates replicated through serography, each plate is mounted onto an intaglio press, applying 20 to 40 tons of pressure, enough to crush an iPhone. Under this immense force, ink is pushed out of the steel grooves and onto the cotton linen surface, forming the raised texture and the distinctive, real money scent that every counterfeit note fails to replicate. And once the intaglio printing is complete, the bill moves on to a completely different layer of security. OVI color shifting ink, a technology guarded like a military secret. OVI ink appears only on denominations $10 and above, yet it is one of the most visually recognizable security features. Tilt the bill slightly, and the number 100 shifts from a copper hue to green right before your eyes. This effect comes from a multi-layer structure containing ultra-fine metallic crystals that act like nano mirrors, reflecting light at precise angles. The technology is so tightly controlled that only a handful of countries and suppliers, primarily SICPA of Switzerland, are authorized to produce it. Even central banks are never allowed to possess the raw ink. They receive only the exact amount required for each print run, and that ink has never existed on any black market. Once the OVI layer has sealed the surface with its signature color-shifting effect, the process still isn't over. The bill moves on to an even more intricate layer of security, one so small that it's nearly invisible to the naked eye: microprinting. Microprinting is the art of hiding text in the most sophisticated way on a US dollar. On the $100 bill, you'll find the phrase, "The United States of America," delicately engraved into Benjamin Franklin's collar, while the tiny USA rests just beneath his portrait. So small, you'll need a magnifying glass to see it clearly. If you're holding a $100 bill, try checking it now and see how sharp your eyes really are. These miniature characters are printed with specialized inks and micron-level engraving plates. To the average person, they look like decorative patterns, but to experts in currency inspection machines, they are the first, fastest, and hardest to fake line of defense against counterfeits. Once the microprinting layer has finished its role as the subtle gatekeeper, the bill moves on to its final stage, the part that is, ironically, the easiest to counterfeit: printing the serial numbers and treasury seals. In this step, a specialized printing system stamps each bill with two unique serial number sequences, giving every note its own identity. At the same time, two important seals are printed on top: the U.S. Treasury seal and the Federal Reserve seal. This is also one of the few elements that criminals can attempt to mimic, since serial numbers use flat ink without raised textures or complex security structures. Passing off a fake is one thing, but getting through quality control is a completely different battle. Right after the identity layer is printed, each bill enters one of the strictest inspection systems in the entire process. Ultra-high-resolution optical sensors scan every millimeter, catching anything from color shifts and ink bleeding to a single misprinted serial digit. Raised ink, color-shifting OVI, and microprinting are analyzed in mere milliseconds. Even the tiniest deviation sends the bill straight to recycling. Finally, a manual inspection team randomly checks bundles to ensure no subtle flaw slips through. Only the bills that pass this brutally strict inspection phase earn the right to move on to the final stage: cutting and packaging. Each sheet of currency is printed in large formats, with 32 complete $100 bills on a single sheet. After inspection, they're fed into an ultra-precise cutting system that slices them into individual notes with exact dimensions of 6.14, 2.61 inches. The blades are so sharp that even a deviation of a few microns can disqualify an entire batch. The finished bills are then stacked into bundles of 100, pressed flat, and grouped into bricks of 1,000. Every brick is tagged with its batch code, production date, and traceability data, all instantly digitized for auditing and storage. The optimal time to harvest hemp is late summer, when more than 6,500 hectares of industrial hemp in the San Luis Valley simultaneously reach ideal height and biological maturity for producing bast fiber and woody hurd. At this stage, specialized harvesters are brought into the fields, machines capable of cutting stalks close to the ground, preserving their full 2.5 to 3.5 meter length, and aligning them in a single direction during operation. This cut and line technique minimizes stem twisting and breakage, reduces bast skin damage, and preserves more than 80% of fiber value right at the field. After cutting, the machine spreads the stalks evenly across the field to ensure a stable retting process. Natural dew retting, driven by moisture and microbial activity. Standard retting takes 2 to 6 weeks, depending on soil humidity, nighttime dew, and temperature fluctuations, all of which affect how quickly the pectin layer bonding the bast and hurd breaks down. By maintaining the integrity and tensile strength of the bast fibers, the proportion of stalks meeting spinning grade quality increases significantly, boosting productivity to over 5 tons of dry stalks per hectare, a level manual labor can hardly achieve at scale. Unlike harvesting hemp for fiber, which requires keeping the stalks long and intact, harvesting hemp for hemp cement, hempcrete doesn't require taking the whole plant. Instead, growers use forage harvesters or specialized hemp decortication harvesters. These machines operate using a high-speed rotary cutting system at the front, slicing the stalks into short segments as soon as they enter the intake. After that, a hammer mill or chopping drum further processes the stalks, breaking them down into small pieces ranging from 5 to 25 millimeters, the optimal size for separating out the hemp hurd, the lightweight woody core used in construction materials. The shredded material is then carried upward by an auger conveyor directly into the machine's rear collection tank, or transferred into a towed trailer for transport to the decortication facility. And now we've arrived at the most exciting part of today's video, the process of transforming hemp into high-performance, next-generation materials. The production of hempcrete begins with separating the woody core from the outer fiber. After harvesting, the hemp stalks are fed into a decorticator, where counter-rotating rollers and crushing drums mechanically break down the stalk, peeling the bast fibers away from the hurd through compression, shear forces, and continuous oscillation. Immediately afterward, a system of screens and air separators automatically filters out short fibers and impurities, retaining only clean, uniformly sized hurd with its structural integrity intact. After being screened, the hurd is fed into a dry mixer to loosen the fibers and increase aeration before combining with the binder. Immediately afterward, hydraulic lime or hydrated lime is added at the standard ratio of 1 part hurd, 1.5 parts binder, and 2 parts water. This ratio is specifically formulated to allow easy shaping and mineralization while preserving the hurd's natural properties, porosity, lightness, and its inherent ability to regulate moisture. After that, the mixture is placed into molds or an in-situ casting system according to the designed thickness. Each layer is lightly compacted and leveled to achieve moderate density, while still maintaining moisture release and air retention capacity. When it comes to real-world construction, Hempcrete is used in two main ways. For projects with standardized designs, builders rely on precast blocks and panels. The mix of hemp hurd and binder is molded, dried, and delivered to the site. Workers simply install these units onto the structural frame and wait for them to set. Fast, clean, and with consistent quality control. The second method is more flexible and suited for projects that require on-site shaping. Hempcrete is used as a lightweight concrete that can be applied or sprayed directly onto a pre-assembled structural frame. Compared to using precast blocks, casting hempcrete in place creates a seamless, monolithic wall with no joints, resulting in better thermal retention, reduced heat loss, and a clearer expression of hempcrete's natural ability to regulate temperature and humidity. A house built with on-site hempcrete typically takes around 7 or 10 days to dry and set. In return, the walls can withstand over 2 hours of continuous fire exposure, are non-combustible, produce no toxic smoke, and do not weaken structurally. In addition, this material continues to absorb CO2 throughout the building's lifespan, helping the house stay cooler in summer and warmer in winter. A key reason why it has already been adopted in more than 40,000 buildings across Europe and North America. Beyond its role as a bio-based construction material, hemp holds another, far more common potential hidden just beneath its soft outer bark: hemp fiber, a natural fiber that is several times stronger than cotton. After several days to weeks of field retting, the dried hemp stalks are transported to the processing facility, marking the official beginning of their transformation from an agricultural crop into an industrial raw material. At the intake gate, any stalks that are curved, have a moisture content above 18%, or are fractured will be rejected. Immediately afterward, the remaining stalks enter the decorticator, but instead of retaining the woody hurd, this entire process is designed to separate and preserve the long bast fibers, the only component used for fiber production. At the critical stage, the bast fiber bundles enter the carding system, where thousands of steel needles on counter-rotating cylinders continuously disentangle, deep clean, and stretch the material. Each hour, a single production line can perform over 20 million micro-carding actions, generating a level of fiber separating force and precision that no manual tool could ever achieve. With every pass through the machinery, the fibers are straightened, fully separated from hurd particles and impurities, and stripped of short, non-standard segments. The result is a stream of smooth, parallelized fiber slivers with stabilized length, officially entering the next stage of high-precision processing. After carding, the sliver is still soft, uneven, and lacks fiber structure, so it is sent through the drawing system. Here, multiple slivers are drafted and combined into a single, uniform strand to equalize density, adjust tension, and stabilize the dimensions of the roving before twisting. Once the sliver is stabilized, it enters the spinning stage, the process that ultimately determines yarn quality. The first step is roving, where the sliver is gently twisted to form a semi-finished strand, strong enough to withstand drafting without breaking. This roving is then transferred to the ring spinning stage, where it is further drawn out, reduced in thickness, and tightly twisted to create the final yarn, meeting industrial standards for tensile strength, fineness, and twist. At modern operating speeds, a single ring spinning machine can produce over 150,000 meters of yarn per hour, transforming loose, disorganized fibers into uniform and stable yarns, ready for the subsequent weaving and dyeing processes. At the end of the production process, the finished fibers are wound into large spools, each stretching from 8 to over 25 kilometers, depending on manufacturing standards. At this stage, hemp fiber is fully processed and technically complete, officially becoming a feedstock for textiles, biocomposites, cellulose engineering, and various forms of industrial reinforcement materials. Leaving the factory, hemp fibers enter supply chains in more than 30 countries, with the fashion industry consuming over half of all output. And although hemp is not yet as mainstream as cotton or polyester, full collections made entirely from hemp fiber have already begun to appear. Few people realize that if somewhere in a landfill, you find a t-shirt that decomposes completely within just 6 to 8 months, there is a good chance it was made from hemp. Even more remarkable, every ton of discarded hemp fiber continues to absorb nearly 2 tons of CO2, creating a net positive environmental impact. Rather than contributing to degradation like most other fibers today,